Very good morning to all of you. My name is Akash Gautam. Work, sorry, I work as a consultant at Qmatic, providing consultancy around Kubernetes and all things cloud native. So the agenda for this session is to talk about container isolation and briefly touch upon the tools and technologies that help us in achieving container isolation. By looking at the title, a very first question one might have is, why we need container isolation? Or maybe aren't the containers isolated enough already by default, right? And to understand this, let's do a quick container 101 and revisit what containers actually are under the hood. So on a given Linux host, containers eventually run as processes in the user space of the system. The difference between any regular process and a container process is that for container process, additional isolation boundaries are created by leveraging kernel features called namespace and control groups. So each container process lives inside a separate namespace and gets its own view of the system. So for network interfaces, for file system, for processes, a container process sees only the things which are inside its namespace. Usually, we don't need to bother about any of these because container engines like Docker or any other CRI provider takes care of doing all the heavy lifting for us behind the scenes and allow us to run containers the way we know it today. But with this, there are some security concerns as well. The Linux kernel, or the host kernel, is shared among all the containers that run on that host. And they all make system calls directly to the same kernel, which is OK as long as the process is within the container boundaries. But what if one of the containers or one of the processes inside the container or application inside the container is under attack, and the attacker is able to break out of the container boundaries, or if the attacker is able to escape the container and run directly on the host? In that case, the attacker can potentially see other processes or containers on the host and compromise them as well. So an attack on a single application or a single container can potentially spill over to each other application or container on the system. To mitigate this risk, better isolation is desired between the application themselves and also between the application and the Linux kernel or the host kernel. This is where container runtime sandboxing comes into picture. So container runtime sandboxing tools basically puts each Kubernetes pod in a separate kernel isolated sandbox, so that even if a process is able to break out of the container boundaries, they only see the kernel of the sandbox and not the host itself. So they basically add an additional layer of separation between the containers and the host kernel. They also get rid of the direct access between the container and the host kernel. A couple of popular tools in this space are Kata Container and another product by Google, which is gvisor. The approach taken by different tools, different runtime sandboxing tools are different, but their end goal is basically the same. Kata Containers, for example, puts each pod in its own lightweight virtual machine. These virtual machines, unlike the general purpose virtual machines, are optimized for running container. So their startup time, their memory footprints, etc., are minimal compared to traditional VMs, which are built for general purpose usage. Another tool in this space is gvisor. So gvisor basically puts each pod in a sandbox that has a kernel running alongside the processes in the user space itself. So gvisor is written in Go. It runs with the containers in the user space itself. They call it user space kernel. It doesn't require any kind of virtualization, unlike Kata containers. And once the pod is inside a gvisor sandbox, all the system calls that the containers running inside the pod makes are filtered through this kernel. And this kernel has limited functionalities and additional control measures to provide protection to the host kernel. So the approach taken by different tools vary, but their end goal is the same. So with this, we are basically trying to get the security and isolation of VMs while still leveraging Kubernetes as a platform. And having sandboxing greatly improves the security postures of our system, but there are some concerns still. What will protect our application or data when the host itself is compromised? What will protect our application from the infrastructure provider, from the device drivers, or from the system admin who logs into the host to upgrade some packages or do some maintenance work? Right. So we operate with the assumption that these entities are trusted. But what if we have additional compliance requirement or additional regulatory requirements, and we want to ensure that our code and data cannot be tampered with even by these super admins who have all the accesses of the host? This is where confidential computing or confidential containers come into picture. The core idea behind confidential computing was to protect data when it is in use inside a server or a system. When we talk about data protection, we talk about protecting data when it is at rest, which can be done by various encryption algorithms. We also talk about protecting data when it is in transit or motion, which can be done by various secure network protocols. But data exists in another state, which is when it's in use inside the memory or in the CPU registers. The idea behind confidential computing is to protect data when it's in use. And this is done by leveraging hardware-isolated environments. So basically, confidential computing requires specialized hardware, and the code and the data are executed in an environment, hardware-enforced environment called trusted execution environment, or for some vendor, it is referred to as enclaves. These enclaves, when they are created, they also generate a cryptographic proof which shows what their initial state was. So along with isolation, another building block of confidential computing is attestation. So we don't trust the trusted execution environment blindly. When they are created, they generate a cryptographic proof, and that proof is signed by the hardware itself. So our trust is on our application, which we built, and on the hardware. We don't need to trust anything that is in between, like the hypervisor, the host OS, or any other third party. So basically, confidential computing is introducing a different trust model, and the trust is only on the root, only on the hardware. Sorry. Yeah. So once we have a trusted execution environment, we also need additional software stack that will do the attestation of this trusted execution environment. And only if the attestation goes through, we unpack our application or code inside this trusted execution environment. So what are the two basic need for confidential computing? We need a specialized hardware that has support for confidential computing. All the major hardware vendors has some kind of confidential computing offering these days. And then we also need a software stack, right, that will take care of creating the trusted execution environment, performing the attestation of that trusted execution environment, managing the keys, and providing any other add-on service based on our specific environment. This is where the confidential containers project come into picture. So it is a CNCF project, relatively new. So what it tries to solve is it provides a standard way of running confidential workloads on Kubernetes. So as we discussed, we need the software stack, and earlier that software stack could be like very vendor specific. So moving from one vendor to another vendor would have been difficult. So therefore, this confidential container software stack is vendor neutral and can be worked. So we can have hardware from different vendor. We can move from one vendor to another as long as we are using confidential containers. And it provides all other services like a key broker service, key management service optionally, and other add-on services. This is like a rough diagram of how confidential containers will look in action. So we have a node here that has support for confidential computing. And similar to Kata containers, confidential containers also put each pod in a virtual machine, but this virtual machine is virtualized out of a hardware that has support for confidential computing. So basically, this virtual machine acts as the trusted execution environment, or it is also referred to as a confidential virtual machine. So here we are basically trying to run an image which is signed which is a confidential image, a confidential workload. So we have signed the image. We are trying to run it in a confidential container environment. So for integrating in the Kubernetes ecosystem, there is a runtime class provided by confidential container. So when we want to deploy our workloads when we want to deploy any confidential workload, we essentially need to specify the runtime class provided by the confidential container stack. And then other things are taken care of for us behind the scenes. So the Kata runtime generates the VM, but it has been extended to support confidential container functionalities. And then there is a attestation agent which runs inside the confidential VM that is created. And then that attestation agent reaches out to the key broker service to get the keys for running the image. But while requesting the keys, the attestation agent also provides the cryptographic proof which shows the state of this confidential VM. And then the key broker service behind the scenes leverages an attestation service and performs the attestation to confirm that the confidential VM can be trusted. And once that attestation goes through, only then it provides the keys for running the image. So this is roughly how different components fall into play. And depending upon the deployment mode used, so this is like this is an environment where the host which is running on bare metal basically, but depending upon different deployment methodology used, the actual component that we get at play can differ. But this Kata runtime or key broker service, all this will mostly be around in all the setups. So we talked about isolation at different layers of the compute stack. We started with process-based isolation, which we get by default. We talked about kernel-based isolation, which we get from Kata containers or gvisor. And then we talked about hardware-based isolation, which we get by using specialized hardware and also leveraging software stacks like confidential containers. So the pattern here is simple. Like as our need for security grows, we push the isolation down the computing stack, starting from process to kernel, all the way down to the hardware. But along with the security, the cost also increases. So where should we do the isolation eventually will depend on what our requirements are. If our industry is such that we need to ensure protection even from the infra provider, or we have compliance or regulatory requirement, or we have very sensitive data or some proprietary code which we cannot afford to lose at any cost, only then we should move the isolation down to the hardware level. And it is worth the effort only when we get sufficient value for the cost and effort that we spent on it. And also there is, so as the isolation increases, there is a hit in the performance as well. So we get better performance by default, the way we run containers by default. But as we introduce more boundaries, more hops, the performance also decreases. Although research done by various hardware providers, confidential computing hardware providers shows that the performance hit is less than 10% in most of the cases, but even that might be a significant difference in some situations. And what's the reason behind this? Like, why we need to push for maximizing security? Why do we need to push the isolation all the way down to the silicon or the hardware, right? So this quote is from a white paper released by Confidential Computing Consortium, which is a project group in Linux Foundation. So this basically sums it up, right? That security is only as strong as the layers below it, meaning that security at any layer can be bypassed if the layer below it is compromised, right? So for maximizing security, we need to reduce the dependency. We need to reduce the entities that we put our trust on and go where we have minimum dependencies, which is all the way down to the hardware. And that is all, I think. With that thought, I think we have come to the end of the talk. These are some very good references which helped me in understanding confidential computing and other things better. Because when I first heard about it, I was very lost. But these are some very good references for anyone interested in reading further about it. And that is all. Thank you so much for your time.
Thank you, Akash. We might have time for a question or two. We don't have one, but I had one actually. So if you do have a question, as always, Slido, QR code, and pop them in there. So obviously you need hardware specific for confidential containers. The cloud providers, are the cloud providers looking into providing the service, or have they started?
Yeah, so most of the major cloud providers, they have some kind of support for confidential computing already. So, and we can also actually run the confidential containers on cloud providers. So if I can maybe go back a little. So here we showed, sorry, is not visible. Okay. So here we showed that the host is a bare metal and the VMs is created out of the bare metal. But these VMs, if we adopt a different deployment model, which is called like peer pod deployment model, these VMs can actually get created on the cloud provider itself. So you will have the VMs created on the confidential VMs created on the cloud provider. Because this confidential containers relies on Kata, and Kata requires nested virtualization, which cloud providers do not support. So we can have like a different deployment method. With that, we can use it on cloud providers as well.
Okay, thanks. We're running out of time, but obviously Akash is going to be around. He's at the Kubernetes booth probably as well. So if you do have any questions, reach out.